Hi, my name is Trevor. Today we're going to be looking at chapter number 7, linear programming. So our lead objective here is we are analyzing short-term pricing and product decisions. Then our component says we need to analyze product mix, including circumstances where linear programming methods are needed to identify optimal solutions. So that's our chapter number 7. So we're still on the same section, decision making. So before we start linear programming, we just have to recap on chapter number 6. On chapter number 6, you looked at what we call limiting factor analysis. Now, in limiting factor analysis, we're talking about each company having a limiting factor. Then if a company has a limiting factor, they need to find ways of best using the limiting factor. Now, limiting factor can be resources, or can be demand constraints, or they can be policy constraints. So because of the different constraints the company can have, or the different limiting factors the company can have, companies need to look at ways of removing the limiting factors. That's the first thing. They need to look at ways of alleviating the limiting factor. If not, then they have to find the best way of using the limiting factor. An example is, if you have a resource limiting factor, say you only have 3,000 labor hours available, then you need to make the best use of the 3,000 labor hours. And how you do that is, you first have to produce the product that contributes more per labor hour. That's what you're basically doing on limiting factor analysis. And on limiting factor analysis, we're making an assumption that we're only going to have resource constraints, and there can only be one limiting factor. So for a company to use limiting factor analysis for short-term decision making, there only has to be one limiting factor. There only has to be one limiting factor. And second point, you can use it for 2 or more products. So limiting factor analysis can only be used if you have one limiting factor, but you can apply it to 2 or more products. Then our aim, limiting factor. The aim was to maximize the profits. The aim was maximizing the profit. So you had to calculate the product that contributes more per limiting factor. Then the product is the one that we have to make first. That's how you maximize the profits. Remember, we said contribution is used to cover fixed costs. So if we start by making the product that contributes more per limiting factor, it means we generate more contribution to cover our fixed costs much faster. Thereby, we're maximizing our profit. And with limiting factor analysis, we had steps that we had to follow. So this is just a recap. So step 1 on limiting factor analysis was we needed to identify the limiting factor. And we said we could only have one limiting factor. So in any question that has to do with limiting factor analysis, it had to be a resource constraint. Either it's labor hours, machine hours, any resource, it has to be a resource constraint. So first of all, we have to identify the limiting factor. Maybe it's machine hours, maybe it's material, maybe it's labor hours. So it had to be a resource constraint. Resource constraint. So constraints in limiting factor analysis, we call them limiting factors. But basically we're talking about the same thing. Anything that restricts the company from making more profits, it's a limiting factor. So step 1, we're identifying the limiting factor. Then step 2 would calculate the contribution per unit. Then step 3 would calculate the contribution per unit per limiting factor. Then would rank the products, would want to rank the products by starting with producing the product that contributes more. Then last now, we'll do our resource allocation, where we would allocate the products based on the resources that we have. So if we rank product A to be the product with the highest contribution per limiting factor. We start by allocating resources to that specific product, in this case product A. So that was our limiting factor analysis. It could only work with one limiting factor. Now when we come to our chapter number 7, linear programming. Now on linear programming can be used if a company has 2 or more limiting factors. To be 2 or more limiting factors. That's point number 1. Then point number 2, our linear programming for a syllabus, we can only use it when we have 2 products. That's for our syllabus. We can only use it if we have 2 products. Because linear programming, we're going to be using mathematical concept, so we need to draw a graph. For a graph, we only have the x and the y-axis. So for our syllabus, we can only have 2 products. So in any question that has to do with 2 or more limiting factors, then we have to use linear programming. But in linear programming, our limiting factors, we're going to call them constraints. So we're still talking about the same thing, but it's different terminology for different concept. So in limiting factor analysis, we call it a limiting factor. For linear programming, we're going to call it a constraint. In our budgeting, we're going to call it a key budget factor. But we're talking about the same thing. What restricts the company from making more profits? What restricts the company from making more profit? So basically, that's how we use linear programming. There has to be 2 or more limiting factors. But for our syllabus, only applicable when we have 2 products. So in any case, if you find a question that has more than 2 products, we cannot be using linear programming. We have to use limiting factor analysis. And you notice that there will only be 1 limiting factor. So from our slide saying linear programming is used to determine profit maximization or cost minimization problem when there is more than 1 constraint. So our aim with linear programming, we have 2 aims. Either we're looking at profit maximization, or we're looking at cost minimization. So with linear programming, we have 2 aims. Either we can use linear programming for profit maximization, or we can use it for cost minimization. But for limiting factor analysis, we only had 1 aim. The aim was for profit maximization. But for linear programming, our aim can be to maximize the profit or to minimize our cost. So that's the theory behind our linear programming. And before we look at how we use linear programming, first we have to revise our basics in maths. Because in linear programming, we'll be looking at simultaneous equations. So on our slide number 2, we want to solve a simultaneous equation. So what you can do is you can stop the video, you try out that question on slide number 2, then we can do it together. So the simultaneous equation is saying 2x minus 3y is equal to 23 and 7x plus 4y is equal to 8. So with our linear programming, we're going to use the graphical approach. Now with the graphical approach, we have to draw a graph. Now on our graph, we have to determine the profit maximization point or the profit minimization, the cost minimization point. So either it's a profit maximization or cost minimization. Now how we determine the optimum pointers? So here I'm just going to use an example. So from our maths, whenever we have a simultaneous equation, what we're looking at is, we're looking at a point where 2 lines meet. So these 2 are equations of a straight line. So where 2 straight lines meet means at this point they have the same x coordinate and they have the same y coordinate. So in our simultaneous equation, we're trying to find the value of x and we're trying to find the value of y. So when these 2 lines meet, the x coordinate and the y coordinate have to be the same. Then with our linear programming, that will be the optimum point where two lines meet. So there have to be two constraints meet. Where those two constraints meet, we need to use linear programming techniques. Then we apply our simultaneous equation. So based on our simultaneous equation, we have to find the x coordinate and the y coordinate to get our optimum point. So solving simultaneous equation, how we solve it, either we have to make the x here, the coefficient of x, we have to make it the same, or the coefficient of y, we have to make it the same. So a coefficient is the number multiplying our variable. So here the coefficient of x here is 2, the coefficient of x here is 7. The coefficient of y is 3, the coefficient of y here is 4. So we have to make the coefficient the same. Either the coefficient of x or the coefficient of y. So here I'm going to choose to make the coefficient of x the same. Now how I do it, I need to look at multiples of 2 and 7. So multiples of 2 and 7, we have 14. That's the lowest common multiple. So what I want is I want to have 14x for both equations. So I take equation 1. Equation 1 I have to multiply it by 7. So 7 times 2x, that's how I get the 14x. Then I also need to multiply equation 2 with 2. So when I say 2 times 7x, I get 14x. But the aim here is to make either the coefficient of x the same or the coefficient of y the same. So since I've used 7 here, I say 7 times 2x, that's 14x. Then 7 times minus 3, it's minus 21y. Then 7 times 23 should be 161. 7 times 23 is 161. We come to the second equation, 2 times 7, 14x, 2 times 4, it's 8y, 2 times 8, it's 16. So now we have equation 3 and we have equation 4. Now since the coefficient of x is now the same, that has to be negative 29, then 161 minus 16 is 145. We divide both sides by negative 29. So 145 divided by negative 29. So our y has to be a negative 5. That's how we solve for y. So this method we call it elimination. So first we had to make the coefficient of x the same. Then we eliminated x because it now has the same coefficient. So if we subtract equation 4 from 3, now we no longer have x. Then we solve for y. Now once we have y is equal to minus 5, now we go back to either equation 1 or equation 2, we substitute. So we now say 2x minus 3 times minus 5 is equal to 23. So this becomes 2x is equal to minus 3 times minus 5, that's a positive 15. We take it to the right hand side. So it's going to be 23 minus 15. Now 23 minus 15, it's equal to 8. So it's 2x is equal to 8. X is equal to 4. So I'll repeat this. Now once we got our answer for y as minus 5, then we substitute y in the first equation. It becomes minus 3 times minus 5, we get a 15. So negative and a negative, we get a positive 15. The positive 15 goes to the right hand side, it becomes a negative. So say 2x is equal to 23 minus 15, and 2x is equal to 8, x is equal to 4. So our answer here is x is equal to 4, y is equal to minus 5. Now what does this mean? Now what we're basically saying is, we have two lines. These two lines are meeting at this point where x is equal to 4 and y is equal to minus 5. That's where those 2 points are meeting. That's why we're using simultaneous equation. Simultaneous equation, we use it when we have two straight lines. We want to find the point where they're meeting. So in this case, they're meeting at the point where the x-coordinate is 4 and the y-coordinate is 5. That's where the two lines are meeting. Then we can also try to do it the other way. So just for practice. So for practice, with the first question we made the question of x the same. Now we want to make the question of y the same. So we need to look at multiples of 3 and 4. The lowest common multiple of 3 and 4 is 12. We can just say 3 times 4, then we get 12. That's the lowest common multiple, which means we can divide 3 into 12, we can divide 4 into 12. So we need to make sure that here we have a 12y, here we also have a 12y. How we do it is we find a number that we can multiply with 3. So here it's 4, and here it's going to be 3. So 4 times 2x, that's 8x minus 12y plus 4 times minus 3y is minus 12. Then 4 times 23 should be 92. 4 times 23 is 92. Say 3 times 7x, that's 21x plus 12y. But 3 times 4y is 12y. 3 times 18 is equal to 24. So we now want to eliminate the y. But here we have minus 12y and we have a positive 12y. Now how we eliminate here, we have to add. Because if we subtract, that will be minus 12y minus plus 12y, which is minus 24. So we have to add. Say 8 plus 21x, that's 29x. And 92 plus 24, 92 plus 24 is 116. And we divide both sides by 29. Notice we still get the same answer, which is 4. So either you make the question of x the same or the question of y the same. We're still going to get the same answer. So you just have to find which one is easier to do. Should you make the question of x the same? Should you make the question of y the same? Now, once we get our x is equal to 4, now we go to substitute in the first equation. Now it's 2 times 4 minus 3y is equal to 23. Now 2 times 4, that's 8. Say 8, we take it to the other side. It becomes minus 3y, 23 minus 8. And minus 3y is equal to 15. So negative 3y, then y is equal to negative 5. So we still get the same coefficient. So with this linear programming, we should be able to solve simultaneous equations. Because in some cases, on our graph, it's not easy to identify the points because our graph will be not as accurate as we would want to. So in a case where it's not easy to get our point on the graph, we have to use simultaneous equation. So to just explain what I'm saying here is, so you might have a scale of say 100, 200, 300. This is 150, 300. So if our lines now are meeting at this point, then on our graph, if it's not that easy to find this x coordinate and to find the y coordinate, it's best to use simultaneous equation. With simultaneous equation, we get the most accurate answer. Because in some cases, our graph will not give us the most accurate answer. So we have to use simultaneous equations. So that's it on simultaneous equations. The next thing is we need to look at another mathematical concept. The other mathematical concept is understanding inequalities. So we're going to use the inequality on slide number 3. The inequality says 5 minus 2x is less than 25. So our inequality can be less than, greater than, less than or equal to, greater than or equal to. So with this inequality, I want you to stop the video. I want you to try to solve for x. I want you to solve for x. Then we can do it together. So in inequality, it's almost similar to an equation. But here we're just saying the left-hand side is less than 25. On an equation, we're saying the left-hand side is equal to the right-hand side. So that's the difference. On an inequality, we say our left-hand side is less than the 25. So to solve this inequality, so we say minus 2x less than 25 minus 5. Comes minus 2x is less than 20. Divide both sides by negative 2. Now x now becomes greater than negative 10. Or x becomes greater than negative 10. So on an inequality, whenever you divide with the negative sign or whenever you multiply with the negative sign, the inequality sign has to change. So if it was less than, it becomes greater than. If it was greater than, it becomes less than. So I'll repeat the concept. We solve an inequality the same way we solve an equation. The only change comes now when we divide with a negative number. The sign has to change. So from less than, it changes to greater than. That's how we solve inequalities. So that's it on our basic maths. Now we need to look at how do we apply the maths in a linear programming question. Now we're going to look at how we use linear programming analysis in a question. We're going to use slide number 4. The question reads, a company produces 2 products in 3 departments. Details are shown below regarding the time per unit in each department, the available hours in each department, and the contribution per unit in each department. Required. Following the procedure for graphical solution, define the optimum production line. To just recap, we said linear programming, we use it when we have 2 products. So for a syllabus, it can only be 2 products. Then number 2, there has to be 2 or more constraints. With 2 or more constraints. So our limiting factor here, we call them constraints. So in linear programming, we call them constraints. In limiting factor analysis, we call them limiting factors. So this is very important. So looking at this question, we have 2 products and we have 3 constraints. Then our aim here is we want to find the optimum production line. So it means our aim here is want to maximize the profit. With linear programming, we said either we're looking at maximizing profit or minimizing cost. Now whenever you get a question on linear programming using the graphical solution, we have to do it in steps. Step 1, we need to define the variables. We need to define the variables. The reason for defining our variables is using the graphical approach. We want our products to be either on the y-axis or to be on the x-axis. So we said we have 2 products, so they have to be either on the x-axis or y-axis. So we need to define which product is on the x-axis, which product is on the y-axis. That's step 1, defining the variables. But in your exam, you might see that it's not necessary, step 1. Although this is the x-axis, if we have product Q, we can just put Q here, we can just put product L here. It's not that necessary, as long as we indicate that this axis is product Q, this axis is product L. But the reason why we have this step is we just want to allocate the x-axis to a different product and the y-axis to the other product. So step 1 will never be examined, but it's necessary in the graphical approach. And we go to step 2. Need to state the objective. Need to state the objective. So for linear programming, we can either have an objective to maximize profit or an objective to minimize cost. So either we're looking at maximizing profit or we're looking at minimizing cost. Now, maximizing profit is the same as maximizing contribution because our fixed costs are constant. So if fixed costs are constant, maximizing profit is just the same as maximizing contribution, because the contribution is then used to cover the fixed cost. Saying is the same. Maximizing profit, same as maximizing contribution. So with this question, our aim is to find the optimum production line. So we want to maximize the contribution. So to maximize the contribution here, we have to look at what is the contribution for product X. So product X has $4 per unit contribution. So we say 4X. We don't know yet how many units we want to produce of X, but we know each unit produces or provides a contribution of $4. Plus, each unit of Y contributes $8, plus 8Y. So we don't know how many units of Y should we produce for us to maximize the contribution. So aim here is want to maximize contribution. So we're saying we need to produce X units and Y units to maximize the contribution. So say 4X plus 8Y is going to be the maximum contribution. So with this whole linear programming, our aim here is now we need to find those X units and Y units that maximize contribution. So there can only be one point that is going to maximize contribution. So it only means there can only be a certain number of X units and a certain number of Y units that are going to maximize our contribution. So step 2 is very important. Either we're maximizing contribution or minimizing cost. So in the exam, you need to make sure that you understand, is the company minimizing cost or is it maximizing contribution? And with some cases, you won't be given the contribution per unit, you just have to calculate it. And we said contribution per unit, it's selling price per unit less variable cost per unit. Then we go to step number 3, step 3. Now on step 3 now we need to define our constraints or state our constraints. Need to state our constraints. So constraint number 1 is in department A. Department A, there are only 11,000 hours available. Department B, 9,000 hours available. Department C, 12,000 hours available. If we produce certain units of X and certain units of Y, we need to be within the constraint. So for department A, we need 8 hours per unit. So we say 8X plus 10Y, because we need 10 hours per unit of X. Then these hours should be less than or equal to 11,000. So I'll explain this. So in department A, since we only have 11,000 hours, and what we're trying to do is we're trying to find the maximum output or the optimum output that is going to maximize our contribution. So there's X units that we're going to produce and the Y units that we're going to produce. Each unit requires 8 hours, and for Y it requires 10 hours. But when we make these units, they should not exceed 11,000 hours, because that's a constraint. We only have 11,000 hours. Then department B, we say 4X plus 10Y should be less than or equal to 9,000. Department C is 12X plus 6Y should be less than or equal to 12,000. So this is department A, department B, department C. In your exam, step number 3 can be asked, but how they ask step number 3 is not like how it's put here in this question. So this question is easy because we can identify that we need 8 hours for X, we need 10 hours for Y. In the exam, the examiner will give you a question, but they won't give you the hours required. You have to calculate the hours required. So we're going to look at those kind of examples. So that's our step number 3. We have our resource constraints A, B, and C. Then always we need to put our non-negativity constraint. negativity. Now with non-negativity, we're saying we cannot produce negative units of x, we cannot produce negative units of y. So our x and our y have to be greater than or equal to 0. So always remember to put this constraint, the non-negativity constraint. So that's our step number 3. We go to step number 4. Our step number 4 is drawing the graph. So for step number 4 at least you need a graph paper. So I'll try my best to just put this graph on the board, but you need a graph paper at least to have an accurate graph. So we're going to look at step number 4 now. We're now going to look at how we draw the graph. So in our exam we're not going to be asked to draw the graph, but then it's important to know how do we come up with the graph. In your exam the graph will be drawn for you, but the examiner might require you to label the lines. So how we draw the graph is, since we have stated our objectives, we have stated our constraints. So in department A the constraint is 11,000 hours, in department B the constraint is 9,000 hours, department C the constraint is 12,000 hours. Want to see how can we represent this on a graph. So to draw a graph of a straight line we only need 2 points. Then we join the 2 points, we come up with a straight line. So how we do it is we use the easiest points. We need a point when x is 0 and we need a point when y is 0. So let's start when x is 0. So when x is 0 here, it means 8 times 0. We only left with 10y is equal to 11,000. Means y will be equal to 1,100. Then we have 1,100 here. So we're saying when x is equal to 0, y is equal to 1,100. Then we do the same thing. Say when y is equal to 0, this equation just becomes 8x is equal to 11,000. Then our x is equal to 11,000 divided by 8, which is 1375. 1375. So that's how you come up with the straight line. Now once you have these 2 points, you just need to join the 2 points. You have a straight line. We go to the second constraint, department B. Now in department B, we also need just 2 points to come up with a straight line. So the easiest points to use are always when x is 0 and when y is 0. You can use other points, but here we're just looking at the easiest points to use. So then when x is 0 here, this becomes 10y is equal to 9,000. Y is therefore equal to 900. Then we do the same thing. Say when y is equal to 0, so when y is equal to 0, it becomes 4x is equal to 9,000. Then our x is equal to 4,000 divided by, x is equal to 9,000 divided by 4. It's 2250. So that's how you come up with the 2 points. And what we need to do is we go to our graph, we just join the 2 points. Then lastly with our department C, we do the same thing. So when x is equal to 0, then 6y is equal to 12,000. Means y is equal to 12,000 divided by 6, which is 2,000. Then we look at when y is equal to 0. Now when y is equal to 0, it becomes 12x is equal to 12,000. Means your x is equal to 1,000. 12x is equal to 12,000. Therefore x is equal to 1,000. So when coming up with our graph, we just need 2 points. Those 2 points, we join them, we come up with a straight line. So here we've done that for A, we've done it for B and for C. So it's always easier to use when x is 0 and when y is 0. It makes it much easier. So in a case where if we're asked to draw the graph, using x is equal to 0 and y is equal to 0 is the fastest way of getting to the 2 points. Because when you say x is equal to 0, you know you've eliminated the x side. You're left with 10y is equal to 11,000. When you say y is equal to 0, you've eliminated 10y. Say 8x is equal to 11,000. So now we need to draw our graph based on those 2 points. When x is 0, y is 1.1. When y is 0, y is 1375. With our other constraint, we said it's called a non-negativity constraint. Now in this case, our non-negativity constraint was saying x and y are greater than or equal to 0. So we don't need to put it down. So you have seen our constraints with Department A, Department B, and Department C. These were resource constraints. Then the non-negativity constraint, it was a demand constraint. We're saying we cannot produce or cannot sell units that are negative. So we can only sell units that are above 0. Can only sell units that are above 0. So the non-negativity constraint, we're going to look at it again, because not all questions are going to sell units that are greater than or equal to 0. With some questions, you're going to have a minimum units that you can sell. Maybe the minimum that you can sell is 100. So our line has to be greater than 100. But for our question here to draw a graph, we just need the 6 points here. Then we can come up with the graph. So now we're just going to look at how do we draw the graph. So you must have a graph paper to just try to put these points down. So I'll try to draw the graph on the board. So now when it comes to drawing the graph, said we already have our 2 points. So this constraint A, B, C, we have 2 points for each of the constraints. With our step number 1, we said we needed to define the variables. So with this question, we have product x and we have product y. So it's easy. So we'll say the x-axis will be product x. Then the y-axis is going to be product y. Here we have the point of origin. So we start with constraint A. So the constraint A, our 2 points says, when x is equal to 0, y is equal to 1.1. So x is equal to 0 on this y-axis. So when x is equal to 0, y is equal to 1.1. So this is just an estimate because I don't have a graph paper. So what I first did here is I looked at what is the maximum value for x. So my maximum value for x, it's 2,250. So here I had 2,500. And the maximum value of y is 2,000. So I had 2,000 here. When you're drawing the graph, you should make sure that at least it fills 3/4 of the graph paper so that at least your answer is more accurate. So for constraint A, saying when x is 0, y is 1.1. Then when y is equal to 0, so y is equal to 0 here, x is 1375. So let's just say we have 1375 here. Then we have to join the 2 points. So that will be constraint A. Let's just put it here. That will be A. Then we go to B. So for B again we have 2 points. Says when x is 0, y is 900. So that will be somewhere here. Then when y is 0, x is 2250. So 2250 will be somewhere here. So we need to join 2 points. So that will be B. And we go to the last constraint, which is C. When x is 0, y is equal to 4,000. So when x is 0, y is 2,000. X is 0 here. Y is 2,000. Then when y is equal to 0, x is equal to 1,000. The pointers here. So this is how the line is. So now we have our three lines. We have A, we have B, and we have C. Now once our three lines are in place, with A, B, and C, then here, because we want to maximize the profit, we first need to know what is the feasible region. So our feasible region is any area that is here. So what you do is you start from the point of origin, you look at which one is the first point that you get to. So here, it's our first point that we get to. Just use a different color. Then from the y-axis, you do the same thing. Look at your first point that you get to. Then now you need to join this. So to join these 2 points, you come here, then you come here, then that's how you get to this point. Saying our possible outcomes, it's either at this point, call it 1, 2, 3, or 4. These are all our possible outcomes. But for linear programming, we can only have one outcome, because we want to find the one that is going to maximize our contribution. So although all of these are possibilities, but our aim is we want to find the one that maximizes the contribution. How we do that? First, we need to come up with an ISO contribution line. We need an ISO contribution line. An ISO contribution line is a line that is similar to the contribution line that we came up with on step number 2. We call that an ISO contribution line. So to just explain on the ISO contribution line a bit, just have to recap what we're talking about. Saying once we have drawn the graph, we have identified that our possible points is point 1, 2, 3, and 4. We said how we do that is, on profit maximization, we start from the point of origin, we look at the first point here, which is this one. From the point of origin, the first point on the y-axis is this one. Then we have to join this. So to join this, we have to first come to this point, then this point. Then our point 1, 2, 3, 4, our possible points. And either we have to find the coordinates of this here, or point 1. So point 1 it's easy because we know it's 0 and 900. We use that to find the total contribution. Remember our contribution line? When you said our objective is to maximize contribution, our objective line was 4x plus 8y is equal to z. Because we didn't know the contribution yet. So we're saying point 1 here is a possibility. So what we can do is we can go put 0 and 900, so we put 0 on the x, we put 900 on the y. We find the contribution. We do the same thing for point 2. We do the same thing for point 3. We do the same thing for point 4. Then we choose the point that is the highest contribution. That will be our optimum point. And now using the graphical approach, what we need to do is we need to draw an ISO contribution line. An ISO contribution line, it's a line that is similar to the contribution line. So we need to come up with an ISO contribution line, a line that is similar to the contribution line. So how we do it is, since we know that we're going to maximize our profit at the point where 4x plus 8y is equal to a certain number, that's the contribution that we're looking for. So what we do is we can come up with any figure for the contribution, because our aim is we just want to draw a line that is similar to the contribution line. By similar, what we're trying to do is we're trying to draw the line that is the same gradient. So that's just our aim, a line that is the same gradient, a line that is similar. So here, let's say I choose a contribution of 2.4. I come up with my x and the y. And we say to draw a line, we need only 2 points. We need to know when x is equal to 0. We need to know when y is equal to 0. When x is equal to 0, 8y is equal to 2.4, means y is equal to 300. When y is equal to 0, then x is equal to 600. So the reason why we have to use when x is equal to 0 and when y is equal to 0, they are very easy to work with. Because when I say when x is equal to 0, I've eliminated the x part. Then 8y is equal to 2.4. The y is 300. When I say y is equal to 0, then I've eliminated the y. And 4x is equal to 2.4. And the x is equal to 600. And we come to our graph. We draw when x is 0, y is 300. So the point is, sorry. Yeah, when x is 0, y is 300, so we have point here. Then when y is 0, x is 600. So this line, we call it an iso contribution line. It's a line that is similar to a contribution line. Let's say I chose a different figure here. I want to see what will be the effect. Let's say instead of using 2,400, I want to see what is the change if we have to use 4,000. Now, if we use 4,000, then when x is equal to 0, 8y is equal to 4,000. Means y is equal to 500. Then when y here is equal to 0, 4x is equal to 4,000. Means x is equal to 1,000. And my points have changed. Now to draw this line, I can say when x is 0, y is 500. Then when y is 0, x is 1,000. Now what I want you to notice about these two lines is, these two lines, they have the same gradient. They are slanting at the same angle. So they have the same gradient. They are slanting at the same angle. So that's why we call them iso contribution lines. They are similar to the contribution line, although they're not the actual contribution line, but they are similar. So any point that, any figure of contribution that we use, we're still going to get the line that is the same gradient. We still get a line with the same gradient. Now once we have this line, we need to slide it. So how we do it is, we need to take this line, we need to slide it out. So you need to have a ruler, you need to have a longer ruler. You slide it out. Then the last point to be touched, either point 1, 2, 3, or 4, the last point that has to be touched will be your iso contribution line. So I'm going to illustrate using the graph that has already been drawn by our textbook. So I'm going to have an illustration of how we're going to slide. But we just have to have a ruler. We have a ruler, then we're going to be sliding outwards. Then the last point that has to be touched is the point that maximizes our profit. And now we're going to use the textbook to illustrate the point. So on our board here, we could not fully illustrate it because our graph was not that accurate. So here in our textbook, we have the profit line already drawn. That's our iso contribution line, the line that is similar to the contribution line. Then our feasible point here is point B, point C, point D, and we have point E. And we said how we come up with these points is, we start from the point of origin, we look at our first point on the y-axis, then again from the point of origin we look at our first point on the x-axis, then we have to join them. So to join them we have to pass through C, then D, then go to E. So these 4 are our possible points. So now what we do is we take our ruler, we put it on the profit line, then we're going to slide our ruler, making sure that we maintain the same gradient. So we slide it, maintaining the same gradient. Then the last point to be touched is our optimum point. So in this question, our last point to be touched is point C. So I'll just repeat that. We're saying we slide our ruler, saying from the iso contribution line, we want to maintain the gradient. Because remember, we said the iso contribution line, it's a line similar to a contribution line. So we slide it, making sure we maintain the gradient. Then here first we touch point D, we touch B, then lastly we're going to touch point C. So point C here is our optimum point. Then from our graph here, to find the coordinates of point C, it's not going to be easy. So just to illustrate, so those 2 are our possible points. But then from our graph, it's not easy to identify what value do we have here on the x-axis. But it's easy to see that here on the y-axis we have 700. So now we need to use simultaneous equation to find the value of the x-coordinate and the y-coordinate. Now we have determined our optimum point, and we notice that our optimum point is C. But then using the graphical approach, it's quite difficult to get with certainty the coordinates of x and the coordinate of y. Now what we need to do now is look at point C, which 2 lines are meeting at point C. So at point C we have department A line meeting with department B line. So we have two straight lines meeting as department A line meeting with department B line. So you can just go back, check in your textbook. Notice that we chose point C to be our optimum point. We said it's the last point to be touched by the ISO contribution line. So that's the point that maximizes our contribution. Then that point, it's when line B, department B and department A meets. Then our constraints for department A, we had 8x plus 10y is equal to 11,000, and we had 4x plus 10y is equal to 9,000. So now we want to find the x coordinate and the y coordinate. Now we have to use our simultaneous equations. Remember when we started the session, we said simultaneous equations are used to find the point where two straight lines meet. So we want to find the x coordinate and the y coordinate. So based on those two, line A and line B, we now want to find the x coordinate and the y coordinate. So this is equation 1, this is equation 2. Said whenever we solve simultaneous equations using elimination, first we have to make the question of x the same or the question of y the same. So what I want you to do is you can stop the video, then you can attempt it, then we do it together. So here we're going to use elimination. So I'll just repeat how elimination works. We have to make either the question of x the same. So here the question of x is 8, of x here it's 4. The question of y the same, the question of y is 10, the question of y is 10. So already with this question it's easy because the question of y is already the same. So we say equation 1 minus equation 2. So 8x minus 4x, we get 4x. 10y minus 10y is 0. 11 minus 9,000, that's 2,000. Then our x becomes 2,000 over 4, which is equal to 500 units. So our x coordinate is 500 units. So from the graph there we could tell that the answer is between 400 and 600, but we could not tell with certainty. Now with the simultaneous equation we get our accurate answer, 500 units. Now once we have the x coordinate, we can go back to substitute. So we go back to equation 1, we say 8 times 500 plus 10y is equal to 11,000. So 8 times 500, that's 4,000. So it's 4,000 y plus 10y is equal to 11,000. Then 10y is equal to, we take the 4,000 to the right hand side. That's 11,000 minus 4,000, which is 7,000. Then y is equal to 700 units. So from our graph there, we can tell that the y coordinate was 700. The one that was a bit difficult to tell was the x coordinate. But now we know that the x coordinate is 500. So we say now profit maximization point is the point where x is equal to 500. The point where x is equal to 500 and where y is equal to 700. That's our profit maximizing point. Then to get the total contribution, based on our step number 2, our objective was to maximize contribution. And we said how we maximize contribution, we have to make x units that contribute $4 per unit, and y units that contribute $8 per unit, we get the contribution. Now we know that to maximize contribution, we need 500 units of x. So we take 4 times 500 plus 8 times 700. So 4 times 500, that's 2,000. Then 8 times 700, that's 5.6. So 5.6 plus 2,000. So the maximum contribution that the company will get is 7,600. How they get the maximum contribution is by producing 500 units of x and 700 units of y. So that's how we use linear programming, using the graphical approach. We do it step by step. So we said our step 1 was to state our variables or define our variables. Defining our variables, we say the reason is we want to give the products to the x-axis or to the y-axis. So this question, it was just easy because we had product x and product y. And our step 2 was to state our objective. We said objective is either to maximize contribution or we're going to minimize the cost. With this question, we wanted to maximize the contribution. And each unit of x was contributing 4, each unit of y was contributing 8. Now step 2 might be asked in the exam. So you should be just able to calculate your contribution per unit. And step 3 is to state the constraints. Now stating the constraints, we just need to know how many hours do you have. So remember, our constraints are going to be resource constraints or demand constraints, or we're going to have both. So we're just stating the constraints. Then step 4 was plotting the graph. To plot the graph, we said we need 2 points, and the easiest way to do it, we say when x is equal to 0 and when y is equal to 0. For exam, we will not be asked to draw the graph, but we might just be given a graph and we're asked which line is this line. So we should be able to draw the graph as well for us to know which line is which. Then our step 5 was to find an optimum point. How we do it here is using the graphical approach. We had to first draw the ISO contribution line, which is said it's a line that is similar to the contribution line. Then we had to slide it out. Then the last point to be touched was the optimum point. Now we're going to look at linear programming and sensitivity analysis. With the sensitivity analysis, we want to identify how a change in one of the input variables would affect our optimum point. So I'm going to explain it using the previous question that we did. From our previous question, our optimum point, we found it when department A line was meeting with department B. Now department A line was 4x plus 10y, 4x or 8x, so it was 8x. 8x plus 10y is equal to 11,000. Then department B was 4x plus 10y is equal to 9,000. So with these 2 points, or these 2 straight lines, when they met, that's where we find our optimum point. And our optimum point, x was equal to 500, then y was equal to 700. So we're going to look at what is the effect of sensitivity analysis. So in sensitivity analysis, the first point that we look at is what we call shadow pricing. Shadow pricing can be explained in 3 ways. The first way to explain shadow pricing is, if we could have 1 more hour in department A, what would happen to our optimum point if we could just have 1 more hour? So if instead of having 11,000 hours, if we could have 11,001 hours, what would happen to our output? Another way of looking at it, if we could have 10,999 hours, what would happen to our contribution? Because remember, we said at x is equal to 500 and when y is equal to 700, that's when we maximize the contribution. So I want to see what is the effect of having 1 more hour, or what is the effect if we don't have 1 more hour. So just basically what you're looking at when you're looking at the shadow price. On the shadow price, we're saying what is the maximum that we're going to pay for an extra resource? What is the maximum that we're going to pay for an extra resource? So because if we increase our hours here, we expect our contribution to also increase. So we want to know how much is our contribution going to increase by. So that's the maximum that we're willing to pay for an extra hour. So we're going to explain that using an illustration. But still on this point, there's 2 lines that provide the optimum output. Those 2 lines have a special name. We call them binding constraints. The 2 points that produce the optimum output. The 2 lines that produce the optimum output, we call them the binding constraints. What it means is, with these 2 lines, we're fully utilizing the resources. Those 2 lines we're fully utilizing the resources. Then department C, which was 12x plus 6y is equal to 12,000. Call this the non-binding constraint. The non-binding constraint. The non-binding constraint. Now I'm going to explain this again, saying the 2 points where we have our optimum output, Those two lines here that produce our optimal output, we call them binding constraints because we are fully utilizing the resources. We call them binding constraints. Then here the other line, which was department C, it's a non-binding constraint, which means we're not fully utilizing the resources. Let's just see if what we're talking about here is true. Let's start with department A. Now in department A, if we say 8 times 500 plus 10 times 700, 8 times 500, that's 4,000, plus 7,000, this becomes 11,000. So it means we are fully utilizing the hours. We are fully utilizing the hours. Let's do the same thing for department B. Now department B, we say 4 times 500 plus 10 times 700. What do we get here? We get 9,000, which also means that we are fully utilizing the resources because we only have 9,000 hours. Let's go to department C. Department C, it's 12 times 500 plus 6 times 700. So 12 times 500, that's 6,000, and 6,000 times 6 times 7, so 6 times 700, that's 4.2 plus 6,000. We're only using 10,200 hours. When how many hours are available? 12,000 hours. Which means here we're not using 1,800 hours. So we say there is a slack in department C. It's a non-binding constraint. So it's very important to remember that whenever you get the optimum point, the two lines that produce the optimum point are always binding constraints, which means you're fully utilizing them. So it means those 2 points are the points that only have the shadow price. I'll repeat that. He's saying the two lines that produce the optimum point. With our previous question, it was department A and department B. Those are the two lines that were meeting at the optimum point. Those two lines are binding constraints. So it's only those two lines that can have a shadow price. Because on a shadow price, we're saying if we get one more unit, if one more hour, how much is our contribution going to increase by? So since we are fully utilizing department A and department B, if we get one more of these hours, we're going to increase our contribution. But let's look at department C. Department C, we're only using 10,200 hours. So already there is slack here. We can actually use 1,800 more hours. So we cannot get a shadow price with the slack resource or with the non-binding constraint. So let's just put that down. Saying the two lines that meet at the optimum point are binding constraints. The two lines that meet at the optimum point are binding constraints. Therefore, the two lines will have a shadow price. The two lines will have a shadow price if both lines are resource constraints. So we're going to look at other examples. Because sometimes the two lines might be, one is a resource constraint, one is a demand constraint. So it's only a resource constraint that can have a shadow price. So we're saying if both the lines are resource constraints. And we said what a shadow price is. A shadow price, we're saying what is the extra contribution that we're going to get by having one more of the resource? What is the extra contribution that we're going to get by having one more unit of the resource? So here with our question that we previously did, Department A and Department B are the only lines that have a shadow price. Department C does not have a shadow price because it's a slack resource. It's a non-binding constraint. So explaining our shadow price, then we can explain it in three ways. So shadow price, we're saying the extra contribution. So the key is the term extra. The extra contribution that we're going to get by having one more unit of the scarce resource. The extra contribution. Then we look at it the opposite. If we didn't have one more of this resource, how much would our contribution reduce by? How much would our contribution reduce by? Then number three, thirdly, and this one is more important. With the third one, we're saying, what is the maximum amount we are willing to pay for one extra resource of the binding constraint. So we can explain it in those three ways. I'll repeat. So shadow price is the extra contribution that we get by having one more unit of the resource, or it can be the reduction in contribution by not having that one unit of resource. Then we can also explain the shadow price by saying it is the maximum amount we are willing to pay for one extra resource of the binding constraint. We're going to use the previous question to see what shadow price is, or to calculate what our shadow price is.